of the periodic table. The periodic table is a display of all the elements known to man. It is organized into groups, which are the vertical columns. They determine the number of valence electrons, the outermost electrons in an atom, and periods, which are the horizontal rows. They determine the number of shells an atom has. The periodic table, which has metallic elements to the left and nonmetals to the right, has certain trends or patterns that determine the atomic radius, ionization energy, electron affinity, and others. And today I'm going to break them down and explain what they are. Before we get into it, however, we must first cover three concepts that connect all the trends of the periodic table. These are effective nuclear charge, electron shielding, and Coulomb's law. So let's begin. Effective nuclear charge is the average nuclear charge that is felt by an individual electron. The effective nuclear charge on an electron is given by the following equation, where Z is the number of protons in the nucleus, the atomic number, and S is the number of electrons between the nucleus and the electron in question, the number of non-valence electrons. The greater the effective nuclear charge of an atom, the more attracted it is to its electrons, and this would result in patterns of ionization energy, electron affinity, and others that we'll discuss. Next, we have electron shielding. Electron shielding describes the decrease in attraction between an electron and the nucleus in any atom with more than one electron shell. The more electron shells there are, the greater the shielding effect experienced by the outermost electrons. Think of it this way: electrons repel each other. The more non-valence electrons you have, the greater the repulsion between them and the valence electrons, and the lower the attraction between the valence electrons and the nucleus. Finally, we have Coulomb's law, the law that states that the strength of the interaction between two electrical charges depends on the magnitude of the charges and the distance between them. In an atom, the attractive force between the nucleus and the electrons depends on the magnitude and the distances between them. The force increases as the nuclear charge increases and decreases as the electrons move farther away. Coulomb's law has the following formula, where F is proportional to the charges of the particles over the distance between them squared, and K is the Coulomb's constant. Now let's get into the trends of the periodic table, starting with atomic radii. The atomic radius is essentially the size of an atom. It is half the distance between two identical atoms that are bonded together. The atomic radius of elements decreases as you go across a period, from left to right. The effective nuclear charge increases, more protons for the same number of energy levels, as we move from left to right across the periodic table, so the nucleus has a greater positive charge. Thus, the entire electron cloud is more strongly attracted and shrinks as you move down a group. As you move down a group, the atomic radius increases due to a larger number of shells. The atom gets bigger. The principal level, N, determines the size of an atom. Add another principal level, and the atoms get much larger in radii. As we move down a family, the attractive force the nucleus exerts on the valence electrons dissipates because of this distance. Now we'll move on to ionization energy, which is the energy required to form an ion by removing electrons. Ions are charged atoms and can be either negative or positive. Ionization energy increases across a period due to the increasing nuclear attraction, making electrons harder to remove. Ionization energy decreases down a group, however. This is mainly due to the shielding effect, which is when the atom's electrons shield the valence electrons from the nucleus's attraction, as mentioned earlier. The increased distance can also lead to a decrease in ionization energy. This relates to the aforementioned Coulomb's law as well. Removing each subsequent electron requires more energy, the second ionization energy, the third ionization energy, etc. Some subsequent ionization energies cost more than others. A huge energy price is paid if the subsequent removal of electrons is from another sublevel, say moving from the p sublevel to the s. Next, we'll talk about electron affinity, which is the energy change that occurs when an electron is acquired by a neutral atom to form anions. It is an atom's attraction or affinity when it comes to attracting said electrons. If the addition of an electron is exothermic, then you'll see a negative sign because energy would have to be released. The greater the attraction between an atom and an electron, the more negative the atom's electron affinity. Some elements have a positive electron affinity, meaning the electrons won't attach to atoms and would need to be placed in a new subshell, which is unfavorable. Across a period, electron affinity increases due to the increasing effective nuclear charge. That means it becomes more negative, giving off more energy. The affinity decreases down a group. That means it becomes more positive, giving off less energy. This happens due to an increased number of shells, resulting in a greater distance between the valence electrons and the nucleus. Now we'll talk about ionic radii, the size of ions. There are two kinds of ions, cations, which are positively charged, and they have lost electrons to become so. They are metallic elements, and their formation results in a decrease in size. This is because of their overall positive charge attracts the electrons and shrinks the atoms. Anions, on the other hand, are negatively charged and have gained electrons to become so. They are non-metallic elements, and their formation results in an increase in size. This is because the addition of electrons results in the shielding effect, and of course, the repulsion of electrons. Ionic radii decrease across a period as metallic character decreases and the effective nuclear charge increases, and increases down a group as the number of shells increases. Electronegativity, which is the measure of the ability of a compound to attract electrons. Electronegativity plays a role in the covalent compounds and determines whether or not they are polar. If the atoms have differing electronegativities, then one atom would tug on the shared electrons more than the other, and the compound would be polar. If their electronegativities are the same, then they would share the electrons equally, and the compound would be nonpolar. Electronegativity increases across a period due to, once again, a greater effective nuclear charge, and decreases down a group due to the shielding effect that inner electrons exert on the valence electrons. This also relates to Coulomb's law, where as you go down a period and the number of shells increases, the attraction experienced by incoming electrons decreases. To conclude, there are 5 main trends in the periodic table that either decrease or increase as we move across from left to right, across a period, and down a group. The shielding effect plays a part in a few trends and shields valence electrons from the nucleus's attraction. The effective nuclear charge is the attraction between positive and negative particles and influences the trends. Coulomb's law states that the force is proportional to the charges of particles over the distance between them squared. Thank you all so much for listening. I hope you learned something today.